USAMO 2024 problem 1. Find all integers n greater than or equal 3 such that the following property holds. If you list the divisors of n factorial in increasing order as 1 equals d1 less than d2 less than dot 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 less than dk equals n factorial. Then we have d2 minus d1 less than or equal d3 minus d2 less than or equal dot 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 less than or equal dk minus 1. Okay, for this problem, I can tell you the most useful idea is what that we should use for this problem. In all years of AMO, we have USAMO. All years of JMO, all years of IMO, International Mathematical Olympiad, all years of BMO, British Mathematical Olympiad is this. Considering small examples. Okay, and we can find the idea. It's not only related to pattern. You should find the idea of the problem. So here we can use a small example because we have only one variable, n. Sometimes we have two variables, for example, n and m. You can apply on both of them or one of them. We should check all of them to see which of them is useful. So here we should start from which n? Okay, n3. Then we should consider 3 factorial. 3 factorial is what? Is 6. So we should write all the divisors. d1 to dk is 1, 2, 3. So let's call this idea 1. 1, 2, 3, 6. And how many divisors do we have? 2 to the 1 times 3 to the 1. You should add 1 to each power and multiply them together. So it's 1 plus 1 times 1 plus 1. We can call it idea 2. The reason is what? Because you can have 2 to the 0, 2 to the 1, 3 to the 0, 3 to the 1. And this is 1, it is 3, it is 2, it is 6. So 4 divisors, so we've not missed any divisor. Now, the difference. 2 minus 1 is 1. Less than or equal 3 minus 2, 1. Less than or equal 6 minus 3, 3. So n3 works. Let's write them. Now let's check n4. For n4, it's 4 factorial, which is 24, which is 2 cubed times 3. If we consider number of divisors, it's 3 plus 1, 4 times 1 plus 1, 2, which is 8. So let's write 1, 2, 3, 4 is a divisor, 5 is not 6. And you can use also Gauss idea. 4 times 6, 24. 3 times what? 24. We call it Gauss idea or rainbow idea. Gauss idea or rainbow idea. Why we call it rainbow? Because we say, okay, 3 times 8, 2 times 12, 1 times 24. Because it looks like rainbow, like this. This product of them 24. Now we can say what? Okay. Well, 2 minus 1 is 1. It's okay. 3 minus 2, 1. 4 minus 3, 1. 6 minus 4, 2. 8 minus 6, 2. 12 minus 8, 4. 24 minus 12 is 12. Okay. So we can say n4 is good again. But we've not found an idea. So let's keep writing. n5. 5 factorial, we should multiply 5 by this number, is 120, which is 2 cubed times 3 to the 1 times 5. And if you write the divisors, it's 1, 2, 3, 4, 5, 6. Number of divisors is equal to 4 times 2 times 2, which is 16. Okay, and there are consecutive numbers. We don't have 7, we have 8. We don't have 9, we have 10. We don't have 11, we have 12. We don't have 13, we don't have 14, we have 15. And if you consider the divisors, the difference 1, 1, 1, 5 minus 4, 1, 1. We can check 8 minus 6, 2. This one is 2, this one is 2, this one is 3. And after 15. So we can check what? 16. 1, 2, 3, 4, 5, 6, 7, 8. From here, you can use Gauss idea. 10 times 12, 8 times 15, 20, 6 times 20, and 5 times 24. So as you can see, the difference here is 5, but the difference here is 4. So that's bad. Because the difference here is 5, the difference here is 4. It should be less than equal this. So 5 is bad. So n5 is the first number that we found. It is bad. Now for n6. For n6, we can write 6 factorial. It's 720. If we multiply this by 6, we have one more 2 and one more 3. 3 squared times 5. So if you write the divisors, let's write them. 1, 2, 3, 4, 5, 6. We don't have 7, 8. We have 8. So the difference 1, 1, 1, 1, 1, 2. We have a 9. That's bad. Okay, so because the difference here is 2, the difference here is 1. It should be less than or equal this. That's a contradiction. So n6 is bad. Now let's check n7. Again, we can write 1, 2, 3, 4 for 7 factorial. 1, 2, 3, 4, 5, 6, 7 is a divisor. 8 also is a divisor because we have 2 times 4. 9 is a divisor, 3 times 6. 10 is a divisor, 2 times 5. 11 is not divisor. 12 is divisor, 3 times 4. 13 is not divisor. 14 is a divisor. 15 also is a divisor, 3 times 5. But the difference 12, this one 2, this one 1. So again, it's bad. So n7 is also bad. So we guess maybe from n5 all numbers are bad. So let's see, and we can see something here. The difference here is 2. The difference here is 1. And here we have a prime that we can, here for example 7, here we don't have 13, we don't have 11. And then after that we have difference 1. So let's generalize this idea. Because it is 13, for n8, do you agree we have same problem? Because 10 is a divisor again, 12 is a divisor, 14 is a divisor, 13 is not, 11 is not, 13 is not. Again, 15 is a divisor. So again, we have exactly same problem. It is 2, it is 1. So until which number we have same problem because of this part? 12 divisor, 13 not, 14 divisor, 15 is a divisor. Until 12, we have same problem. So we said 3, 4 are good. So n7 bad, n8 bad, 2 and 12 bad. Now let's check 13. So for 13 we have all numbers 10, 11, 12, 13, 14, 15 is the divisor, 16 is the divisor, 8 times 2 in 13 factorial. 17 we don't have 17. So now the difference is 2. We have 18, we don't have again 19. 20 is a divisor, 21 is also a divisor. So again, we have same problem, the difference 2, the difference 1. So from n13 to n what? All these numbers we can say they are bad. 18, 20, until 18 factorial. Because until 18 factorial, we have 18, we have 20, we have 21 as divisors. So 2 less than or equal 1. Now, so we are jumping between primes. First, we consider 13. Now, we prove this until 19. Now, we should check 19. 1, 2 to 19, all divisors. All of them are divisors. 20, 21, 22. 23 is not a divisor, okay? 23 is not a divisor. Now, we can check what? We can check 24 is a divisor. 25 is a divisor. So, again, the difference is 2. The difference is 1. So, we proved until 22. All of them are bad. Now we want to generalize this idea. Let's keep checking like this for some other numbers. For n23, we know 1 to 23 is good. 24, 25, 26, 27, all of them are divisors. 29 is not divisor, 30 is divisor 31, not divisor 32, 33. So sometimes, for example, when you want, you find a prime, in next step we have difference one, but sometimes like this, we have a prime, and then next one is not prime. So as you can see, the difference here is 2, the difference here is 1. Again, that's a contradiction. So we proved until 30 that these numbers are prime. Now I want to generalize this idea. Okay, so now we should check N31. So as you can see, in each step we prove, for example, until 1 less than this prime. We proved until 12, then we checked 13, then we proved until 18, 1 less than 19, then we've checked 19, and we proved until 23, until 22, then we checked 23, we proved until 30, 31. These are the primes that we are jumping between them, okay? Now I want to generalize this idea. Suppose that we proved until p minus 1, which p is prime, okay? And p is at least, we can say, 31, okay? So we know all numbers, we know n3 is good, 4 is good, 5 not good, as we said here, 6 not good. All these numbers are bad. We can say somehow it's similar to induction. Until p minus 1, all of them are bad, and p is at least 31. Now we want to consider p, and we want to see we can cover until which prime. So if we consider 1, 2, 2, 3 to p minus 1, it's not like, let me write divisors. Our divisors, now let's consider n p. We know it's bad. Now we want to check this. So 1 is a divisor, 2 is a divisor, 3 is a divisor, 4 is a divisor, all of them. P minus 1 is a divisor. And p also is a divisor. Now, again, we want to do exactly the same thing. For example, we said, okay, 23, we wanted to check 23. We wrote until the first prime that we had. So, can you tell me first prime after p? We can say it is in which interval? By Bertrand's postulate, we can say what? If n is greater than 3, there always exists at least a prime number p with p greater than n less than 2n minus 2. So, because I want to find first prime after p, we know there exists a prime q which is greater than p and less than 2p minus 2. So let's consider this prime q. We know that we don't have this q in our... q is not a divisor of p factorial, okay? Because q is a prime. So now let's check q minus 1. Q plus 1, now we have this difference, 2. Then I want to check if we have q plus 2, then here the difference 1, and we can reach contradiction. If we don't have q plus 2, then I want to say we have q plus 3, and we have q plus 4, because these three numbers, all of them cannot be prime. Why? You should consider mod 3. Okay? So, let me explain this part completely. So, here, let's focus on q. We don't have q. I want to prove we have q minus 1 and q plus 1. Let's prove this part first. I want to say we have q minus 1, we don't have q, we have q plus 1. Okay, let's prove this part. It is our claim 1, our first claim. But you know q is odd. Why? Because we know p, we said p is at least 31. So the only even prime is 2. So q is also greater than p. So q is greater than 31. So q is odd. So q minus 1 is even. Q plus 1 is even. We can say what? We can say, okay, we can write q minus 1 as 2 times q minus 1 over 2. Because we have p factorial, we know we have 2. And q minus 1 over 2, again, we want to say we have this, and it is not equal to 2. Why? It is not equal to 2 because q minus 1 over 2 If it is equal to 2, then q will be 5. And we know q is at least 31. Q is greater than 31, so it is larger than 2. So if we consider p factorial as 1 times 2, we have q minus 1 over 2. Why it is less than p? Because we know that q is at most strictly less than 2p minus 2, so we can write 2p minus 3. So q minus 1 over 2 is at most 2p minus 3 minus 1 over 2, which is 2p minus 4 over 2, which is p minus 2. Okay, so we can say we have these two numbers. We can use exactly same approach for this one. That's why we have q plus 1. Again, you say 2 times q plus 1 over 2. We know q is greater than 31, and because greater than p, p is at least 31, and q is less than 2p minus 2, or less than or equal to p minus 3. So we can say q is at least what? Next prime after 31 is what? 33, 35, 37. And you don't need to write until 31. If you write also for, if you check also for a smaller primes, you can reach same proof. It is at most 2p minus 3. So we can say q plus 1 over 2 is at least 38 over 2, 19, and at most 2p minus 3 plus 1, 2p minus 2, and 2p minus 2 over 2 is p minus 1, so that's good. We have this, okay? So we have q plus 1 as an even number. Now, in next step, we should check what claim 2. So we know q minus 1, we have q minus 1. We don't have q. We have q plus 1. Now I want to check q plus 2. If you have q plus 2, the problem will be solved. Okay, if. So instead of claim, let's write two cases. If you have q plus 2, case 1, then that's a contradiction, because the difference here is 2, and the difference here is 1, if q plus 2 is a divisor. Case 2. Suppose q plus 1 is not a divisor, so q is a prime. Q plus 1, we have q plus 1, we don't have q plus 2. I want to prove we have q plus 3. Okay? So for q plus 3, I want to prove this. We can call it claim 2. We have this. The reason is what? We know q is at least, we said 37, and at most 2p minus 3. So q plus 3, I want to write q plus 3 as, because it is even 2 times q plus 3 over 2. So q plus 3 over 2 is at least 40 over 220. You know that's good. At most 2p minus 3 plus this, at most p. And again, we can say it's good because this one is between 1 to p and is not equal to 2. So if we write 1 to p, we have 1, 2 to q plus 3 over 2 to p. So we have this number, okay? The proof was similar to this one and this one. Okay, so let's write what we have. Q minus 1, we have q. Let me write with other color. Q minus 1, we have this as a divisor. We don't have this. We have this one as divisor. And we said we want to consider this one. We don't have this. Case 2. Q plus 3. We have this. If we have q plus 4, again we can reach contradiction if we have q plus 4. And my claim is that we have q plus 4. And we can reach contradiction. We can call it claim 3. So let's prove claim 3. I want to say we have q plus 4. The proof is what? Let's use contradiction. Suppose we don't have q plus 4, okay? Now, I said q is prime. And q plus 2, so we don't have q plus 4, we don't have q plus 2, we don't have q plus 4. I know that one of them should be multiple of 3. Why? Because we know q is prime and is greater than equal 37. If q cannot be 0 mod 3. If you consider mod 3, it can be 1 or 2. If it is 1, this one is 3 and it's multiple of 3. If it is 2, this one is 6 and is congruent to 0, mod 3 congruent to 0. So one of them should be multiple of 3, and because we can say q is not multiple of 3, q plus 2 is multiple of 3, or q plus 4. So let's consider these two cases. If 3 divides q plus 2, case 2 is what? If 3 divides q plus 4. In this case, we can write q plus 2 is equal to, for example, 3t. Or we can write it as 3q plus 2 over 3. I want to say that we have this divisor. We have this is a divisor for p factorial. Why? Because I want to say, we see both of them, we know that we have 3. I want to say that q plus 2 over 3 is another number to p. So let's prove this. We can say we had q is at most 37, at most 2p minus 3. And q plus 2 over 3. Q plus 2 over 3 is at least 37 plus 2, 39 over 3, 13. And at most 2p minus 3 plus 2, 2p minus 1 over 3. I want to prove why, if I prove this number, we know it is greater than 13, so it is not equal to 3. I want to say that we have these two elements. I should prove this one is less than p. So I should prove why this one is at most p. So it is equivalent to what? If we multiply both sides by 3, 2p minus 1 less than or equal to 3p, it is equivalent that p is at least negative 1, which is correct. Okay, so for this case, we reach contradiction because we proved that we have q plus 2 as a divisor. But we know that q plus 2 is not divisor. By this part, by the claim 1 that we claim to case 2. We are in case 2 and we said, okay, we don't have q plus 2. In case 1, we said we have q plus 2. Now let's consider second case. Similarly, we can consider second case here. Again, I want to say q here, when q plus 4 is multiple of 3, we can write it as this, and we can say both of them are different numbers from 1 to p. So 1, 2, 3. I want to prove why we can see q plus 4 over 3 until p. So again, we can say like this one. Q is at least 37, at most 2p minus 3. So q plus 4 over 3 is at most 41 over 3. So it is greater than 3 at most. 2p minus 3 plus 4 over 3, which is 2p plus 1 over 3. And I want to prove why this number is less than or equal to p. Then we can say we have q plus 4 over 3 between 1 to p. So why it is less than or equal to p? Exactly like this. So if you multiply both sides by 3p, so it is equivalent. If you subtract 2p from both sides, so it is equivalent that p is at least 1, so all of them are correct. So again, we reach contradiction because q plus 4 is a divisor, so we can't have this case, okay, as claim 3. So we proved claim 3, and now the difference here is 2, the difference here is 1, and 2 is not less than or equal 1, so we reach contradiction, so we proved. Again, until q minus 1, we proved all of them. So from this prime until next prime, we proved, until next prime less than 1, we proved. Then from q to next prime less than or equal that, we proved. Like what? For example, we proved until 31 minus 1, 30. Then by checking 31, we proved until next prime, 36 minus 1. Again, by same approach, you said, okay, for 37, if we consider 37, we can prove it until next prime, 40, then 41, and so on. Okay, by this approach. Now let me tell you a similar problem that in last IMO we had similar problem. That problem was related to divisors, and again a small example. So here we considered a small example, we considered number of divisors, we considered ghost idea or rainbow idea, and we considered Bertrand's postulate and these things. Okay, so let me tell you the homework is what. You can try this one as homework one, first problem of last IMO 2023. Again, we have divisors, we have something similar to this, and you can use similar approach. So it seems what? If you solve last IMO, last AMO, USAMO, JMO, then you can see the background ideas are repeated, okay? So for next year, for preparing for IMO or AMO, next year of AMO, JMO, AIME, if you want to know these background ideas are what in geometry, algebra, number theory, and combinatorics, as I said before, feel free to send message to my WhatsApp number in the description.